This is homework 2, part A, question 1. Derive the time-dependent heat diffusion equation for a uniform linear bar assuming constant thermal diffusivity. So, what does that look like? First, I'm going to quickly draw like a uniform bar, just so that way then we can have a better visualization of this. So let's say that we are heating up this bar across two ends, and we're trying to find, we're noticing, we want to look at like this position right here, x prime. Let me make that bigger. We see this position right here, x prime. Also, I want to remind you, this is just the problem written out, nothing else on here. I do have my notebook here, but that's just bullet pointed to help keep me on track. So we're looking at this position right here, x prime on this metal bar. And let's say that it's specifically then, like, we want to look at like this section here. So we know that the starting section of, a heat flux that's going in, or Qn, this is supposed to be Qn, I don't know if you can kind of see that. Qn, it's going into this section here of the bar that we're looking at. Will then go out over here. This is across, let's say like we're going across the metal bar. Any position along this bar is some position of x. So at this point we're looking at x prime, because we want to look at this section right here. So x prime is the starting where the heat flux is going in that we're looking at, and heat flux is then going out. So then this difference here from x prime to where heat flux is going out of the section of the bar that we're looking at will be known as dx. And essentially there actually is a relationship we can use to help kind of better bring this together and describe what, where when you're trying to look at heat flux going in and out of a certain section of, in this case, a uniform metal bar, that is described by the law, Fourier's law, which is basically a law that, again, it describes heat flux. Specifically for this, I'll write it out, that how it relates to a uniform linear bar, but it's Fourier's law. It describes heat flux, which is what we're looking at here when heat flux going in and heat flux going out. This section of the bar starting at x prime to some position a little further along of that section. So Fourier's law, spelled F-U-R-I-E-R'(S), law. And essentially it just says that Qn is equal to Qx prime, which is then equal to negative K, that's a constant, times the cross-sectional area of the bar, which is A, times the change in temperature over the change of time being evaluated at x prime. So that's for the heat flux going in at that section of the bar. So then what about heat flux going out of that section of the bar? So then Fourier's law also tells us that heat flux going out will be equal to Q prime plus dx. Dx, again, being that difference from when we're looking at like this section of the bar right here, right? You have your first position of where heat flux is going in, x prime, plus that whole difference to whatever position that is, where heat flux, that we're saying that's the end of the section. That's what we're looking at for the heat flux going out of that section of the bar. Therefore, saying that x prime plus dx helps us relate to what heat flux out is, which then that is then also again equal to negative K, the constant, times the cross-sectional area of the bar, times the change in temperature over the change in time being evaluated at x is equal to x prime now plus dx, because again we're saying that for heat flux out it's x prime plus dx, whereas heat flux going in it's just x prime because it's just that position there. So the last part of Fourier's law then also says that Q net is equal to the heat flux going in minus the heat flux going out. This relationship then tells us that because of this relationship, we then can know that Q out will be, oh my god, I spelled that wrong. Will be, Q out will be positive. Q out will be positive, because if Q out is already a negative and it's being subtracted from Q in to get the heat flux, the net heat flux of that metal bar at that section, it has to be positive. It's going to end up being positive. So therefore, then we kind of can then just say Q out is going to be positive. So from this, again, we need to derive the time-dependent heat diffusion equation for a uniform linear bar, assuming a constant thermal diffusivity. That's a lot. We're going to break that down. But essentially, we want to know the evolution of the temperature inside this part right here, or that section of the metal bar that we're looking at. I'm just going to quickly go with my little red expo marker to kind of show that, like, can you see that? Kind of. Anyway, but we're looking at this section right here, and that is we're looking at the evolution of temperature inside this part right here of the bar, that told dx. So we need to then set up a energy balance, or some might call it a conservation energy equation. I'm going to call it an energy balance for short, just because it's easier for me. So from that, we then can go, and we know a few things. First and foremost, we know that, again, since we're trying to derive the time-dependent heat diffusion equation, that dt, or the change in temperature over the change of time, is going to automatically be on the left-hand side. So I'm trying to think of where it's going. I'm going to put it right here. So we're going to have this big dt over little dt times a few other constants, or not constants, but other variables we have to take into account. Is a metal bar, so there's going to be some type of density. Did not know the whiteboard does that. Let me be careful. So there's going to be some type of density associated with that metal bar. That does not look like, let me just, am I like tripping? Why does that look weird? There we go. That's going to be density. So there's some density associated with that metal bar. There's going to be some specific heat associated with that metal bar. And then we also need to take into account the cross-sectional area of that metal bar, but also the total amount of that bar, aka dx, that we're looking at, which would technically be the cross-sectional area times dx, would give us dV, or the volume of that section of the metal bar. I'm not going to put it as dV. I'm going to keep it as the cross-sectional area times dx, just to keep it simple for us. So it's going to be area dx. Okay, so now we have the left-hand side done, as we're accounting for density, specific heat, the volume of that section of there in relation, also with the change in temperature over the change of time. So now we also know that essentially we're kind of looking at like heat flux, right? So it's Q net. So technically we would have this be equal to Q net, which we then know that Q net over here is Q in, or heat flux in, minus heat flux out. Essentially heat flux in plus heat flux out, because again, heat flux out has to be positive. So we can actually break this apart a little more, and now substitute in these two equations into this equation that will be on the right-hand side of our energy balance. So let me go into that now. So essentially, sorry, thought I heard something. So we're going to have negative Ka dt over the little dt being evaluated at x equals x prime, plus Ka dt over little dt being evaluated at x equals to x prime plus dx. Okay. Try to make sure I'm not blocking the way for this. So as we can see here, what are something that we can kind of, try to make this problem, try to whittle it down a little bit. First thing, we know that the cross-sectional area is not going to change. So that means that A is going to become constant because it's nothing's changing. It's not the cross-sectional area, the area of the metal bar is not changing. It's a uniform linear bar, so it's not changing. So we can, because of that, we can then eliminate it from the problem, like so. And then we can also say that K is also, we could say that like K is not dependent on temperature. So we could then be able to pull K out of both sides of this to then, simplify it a little bit more, if that makes sense. So I'm gonna go here and then do T over this times density, specific heat, and then this will be K. And then let me actually make this, I need all the space I can get. Okay, and then this is going to be negative dt over little dt being evaluated at x equals x prime plus big dt over little dt being evaluated at x plus dx. And then that is going to be over dx. Okay, now we have this simplified down a little more for us. And you know what? Looking at this actually reminds me of a second derivative. So since it looks like a second derivative, I think we could say it's a second derivative. So since we know, or we could say that it's a second derivative, we can then say that it's going to then kind of simplify. This will simplify down to essentially just being K times d squared dt over dx squared. So, because again, when we see that it looks like a second derivative, we could just make that assumption and then we can turn it into this. So then from there, we then can say, or we then can kind of simplify it further to just get dt big big T, big T over little, oh my gosh, dt big, oh my gosh, change in temperature over change in time. We can get that to just being on one side of this equation. So that way then we could then be able to have derived the time-dependent heat diffusion equation for a uniform linear bar. And at that point, we would be assuming a constant thermal diffusivity because essentially, since density is not changing, specific heat isn't really changing, and we have this K, which is a constant as well, those are all constants. Therefore, when we put that onto the other side, we're gonna see something. And that will get into the thermodiffusivity part that we need to make sure that that's constant, that the question's asking us to look at. So for that, we then can do this here, which is then going to be K over density times specific heat in relation to d squared T over dx squared. And here we go. Now we have it that we derived the time-dependent heat diffusion equation for a uniform linear bar, because again we have change in temperature with relation to the change in time, with the heat thermal diffusivity, because this equals thermal diffusivity, or what we can now know it as alpha. right there. Let me quickly write that. Yeah, and this essentially gets us like I said, the time-dependent heat diffusion equation with a constant thermal diffusivity, because like we said, K is constant, density is constant, and specific heat is constant as well. And thermal diffusivity's units is actually meters squared per second. So yeah. So then let me rewrite this down here. There we go.